Bismillahirrahmanirrahim. Hello everyone, I'm Mohammad Fazel Vafadar, a student of electrical engineering from Kent University of Technology. I'm going to talk to you about the optical properties of gallium arsenide thin film with embedded plasmonic nanoparticles done under supervision of Dr. Zahra Arefinia from University of Tabriz. To start with, I'll talk about the scattering and absorption cross-sections of nanoparticles embedded in gallium arsenide. Then I'll explain electric field around MMP embedded in gallium arsenide. After that, I'll explain the optical absorption modeling of gallium arsenide thin film embedding nanoparticles. And finally, I'll present the results of analytical modeling. Because of the presence of free electrons in the conduction band of metal, nanoparticles can act as strong scatterers of light at wavelengths near the plasma resonance. The scattering and absorption cross-sections are given by these equations, where R0 is the radius of nanoparticles and alpha is the polarizability of nanoparticles. For a nanoparticle with diameter well below light wavelength described with point dipole model, the field on the nanoparticle is uniform and can be expressed by Rayleigh approximation as this. For a larger MMP, the multipolar modes have to be considered and the polarizability is computed by an expansion of the first mode of my formalism as this. Okay. The concentration of electric field around a single standalone MMP has been analytically calculated in this paper as this equation, that ER and E theta are the unit vectors of polar coordinate. The optical properties of a regular pattern of nanoparticles embedded in photoactive layer of solar cell can be calculated by exact numerical simulations. The numerical simulations solve the Maxwell equations for a few nanoparticles by defining their geometry explicitly using FDDT approach, boundary element method, or discrete dipole approximation. But in this case of irregularly embedded, like this figure, irregularly embedded nanoparticle, numerical approaches are less tractable because the calculation time heavily depends on the size of system. In this case, the use of analytical approaches which relies on the effective medium theory are very efficient. In the effective medium theory, a heterogeneous material formed by MMP and surrounding media is replaced by a homogeneous material like this figure with an effective dielectric function which exhibits the same dielectric polarization upon light illumination. One of the most famous effective medium theory is the Maxwell-Garnet approximation derived from the Clausius-Mosotti formula or the Lorentz relations. It's only valid for the nanoparticles with a small and low concentration. The Maxwell-Garnet effective medium theory can't explain the optical properties of a medium with embedded resonant plasmonic nanoparticle with radius larger than 10 nanometer. Indeed, with increasing the size of MMP, the interaction between nanoparticles or higher multipolar contribution should be considered. Hinsen and Fedorov, with considering a sufficient number of higher order multiples, obtained the effective dielectric function as this equation, where Gz is obtained from the corrected Clausius-Mosotti formula by considering the dipolar, quadruple, and higher order term of each nanoparticle as these equations, where F is the volume fraction of nanoparticle, An and Bn are constants, and finally Optical absorption of gallium arsenide thin film with embedded nanoparticles is obtained by effective dielectric function as this equation. Okay, now let's discuss about the results. Slide shows the normalized scattering and absorption cross-section, which for the silver nanoparticles embedded in gallium arsenide. It's seen that for the smallest nanoparticles, cross-section, scattering cross-section is less than absorption cross-section. But as the nanoparticle radius increases, scattering cross-sections grows, and for the radius larger than 80 nanometers, scattering cross-section will be much more than absorption cross-section. Okay. The effect of various metals of gold, silver, and aluminum and the normalized scattering and absorption cross-section of nanoparticles is shown in this figure. The peak of cross-sections of gold shows the highest and aluminum shows the smallest. Also, the blue shift of dipolar plasmon resonance is seen for aluminum. These figures show the calculated electric field outside the aluminum and gold nanoparticles at the wavelengths of 510 nanometers as a function of distance from the center of nanoparticles. Aluminum nanoparticles embedded in gallium arsenide exhibit much stronger electric field compared to the gold nanoparticles, because the wavelength of 510 nanometers is the plasmon resonance for aluminum, not gold nanoparticles. And finally, the last slide shows the real and imaginary parts of effective complex dielectric function of nanoparticles embedded in gallium arsenide for different metals of gold, silver, aluminum, and copper with a radius of 80 nanometer and a volume fraction of 5%. To see the effect of nanoparticles, the electric function of gallium arsenide without nanoparticles shown with black curve. It's seen that there are some peaks related to the contribution of dipolar, quadrupole, and octupole plasmon modes in the dielectric function. Broadening of plasmon band, and less amplitude of aluminum nanoparticle, and the highest amplitude of plasmon for gold nanoparticle are also seen. Indeed, large damping coefficient of free electrons for aluminum nanoparticles lead to the broadening of plasmon band and increasing of full width at half maximum. Therefore, employing gold nanoparticles into gallium arsenide increases the absorption of gallium arsenide, and the results improve the photovoltaic parameters. Thank you very much for listening. I hope you have found the talk useful. Have a nice day.